it takes, to state it properly, it takes the notion of normalization as clear from its name, but in fact, you can state it without it by saying that in a sense, it's very similar to primitive element theorem. So primitive element theorem tells us that if you have a finite extension, then K is generated by a single element, which is called primitive element in the field K, big. And then if you have an of X containing of Y, this corresponds to a map from X to Y. It turns out that O of X there exists an element, there exists alpha in of X such that which is primitive, alpha is primitive in K of X in the field of rational functions over K of Y, and also O of X is finite over this of Y with the root alpha, with the element alpha added. So this is more or less the idea. You see that the Noether normalization lemma is essentially a lemma about, it's a version of primitive element theorem given for rings and not for fields. But I won't do it like that. I will explain normalization because I think it's geometrically more clear if you do it like that. So there are some things I wanted to repeat. Okay, this is what we already had. Sorry, it's lecture 15, of course, not lecture 14. But the Noether normalization, there was a couple of statements which we which we have already seen. So the first proposition, suppose you have X inside Cn, and Z1 dot Zn are coordinates. Okay, we can renumber these coordinates in such a way that Z1 dot Zk are bases of transcendence, so transcendence bases. Of K of X. So how you do that? It's clear that all functions are generated by all Z. This means that this field is generated by all of those Z. Some of them have algebraic relations, others don't. So we start from the first, add the second if it has algebraic, if it has no algebraic relations. If it has, we just drop it and renumber so that the first, which has no algebraic relation, which is algebraically independent from Z1, is number 2. Then the third, which has algebraic independence, will be number 3, and so on. This way we have this transcendence basis. And then we have a projection from Cn to Cn minus 1. But we do a certain linear change. P, namely, we, let's better say it like that, that we take Zn plus lambda sum of lambda I Zi from I equal to Z1 to K. This is called Zn prime. And alpha lambda I are generic. Then Zn prime is root of monic polynomial, is finite over C in Z of Z1 dot Zk. We consider this as a subring in OX, and this is an element in this ring. So it is a root of monic polynomial inside this ring with coefficients in that subring. This precisely means that this element is finite. This is something we had last time, and I'm not going to repeat it, but it has this nice version of Noether normalization lemma. So you have, let's say, reducible. Next slide, I will explain how to do it with non-reducible. Something we mentioned last time, but it was not in slides. Okay. So we take x inside Cn, coordinates z1 dot 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 zn, and to assume that z1 dot 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 zk is transcendence basis in the field of fractions. As I explained, we can always assume that. Then there exists a linear coordinate change. Similar to that, we take zk plus I is equal to prime. This is a new coordinate. Sum like here, it will be from I, like let's call it kite j, from I equal to z to 1 to j, and then you have a lambda I plus, sorry, to k, of course, I plus I and k. The these coefficients are numbered by two numbers. Zi plus zk plus j. So we shift each coordinate by some linear transform along the first k coordinates, such that all zi k plus j prime are finite over C of Z1 dot dot Zk. And the proof is the same. You can use induction on, or just without induction. You know that after you change your, you modify your last coordinates by adding the first k coordinates with coefficients, becomes finite, so you can do it with each of your coordinates separately, even without induction. Am I clear? No? So again, you have, what we have from this proposition is that every coordinate will become finite over the first k coordinates if we modify this coordinate a little bit by adding lambda I times the first coordinate. We can do it with all coordinates except the first the first k. And this would do it. We just take a linear change, and then the ring of all regular functions becomes finite over this. Yeah, of course I did, it should be not ZA, but ZK. ZK plus J. Because we replace sorry, it should be I here, a Zn here, and I here. And here you have prime all the time, and here you have no prime, sorry. Anyway, you have linear coordinate change, and it becomes finite. It was correct on slides and slightly incorrect on the blackboard. So you do this linear change several times to obtain that the set of coordinates which are algebraically independent, and the rest of coordinates are finally depending on this first k coordinates. So last time we did it with just one, and then it will be done with all of them inductively step by step. Okay. So we just, how we obtain this corollary from this proposition, the easiest way is just to say that you can always have a finite projection from the last coordinates to the rest. This will be fine because the last coordinates is expressed with the first k in a finite way. And then you just repeat it over and over because composition of finite is finite, and this means that your map from x to c power k will be also finite, which you obtain it by iterating this construction. Okay. Now let's do this theorem for non-necessarily. So here I was speaking about transcendence basis and such things that makes very little sense if your ring has zero divisors. So now let's do that with general ring, which might have zero divisors, just to have it more general. So proposition. Okay. So we have x inside Cn. It's again a fine variety. And k is transcendence degree. So it's maximal transcendence degree because you can have several components which have different number with different ring of fields of fractions. So it's maximal transcendence degree of all irreducible components. Of x. Then there exists a projection, like let's do a linear coordinate change. Then there exists linear coordinate change. And here I should again choose all lambdas. Zi prime is by construction equal to, by definition equal to Zi plus sum. I would just copy the indices because I can't remember them from j equal 1 to k, n minus k, sorry, n minus k. And here we have lambda j. This is the same as should be written here, in fact. J plus k times z j plus k. This is our new linear coordinate change, which is like, it's a cumulative result of the coordinate changes which are prescribed by this proposition term by term. Okay, this is our now we define projection. Then p to the first k coordinates from x to ck to first k coordinates is found when lambda with this should be actually also j and k. Lambda j and k are generic, or j plus, well, indices where lambdas, lambda something are generic. So you do your linear changes step by step. So it should be j plus k and I. J plus k and I. Okay. In other words, all coordinate functions from starting from k plus 1 to n are expressed on each of your, well, are generate a finitely generated model over the ring of X. Since we cannot do, there are zero divisors, this is the only way we can do it, because for monic polynomials it will what, well, you can do it with monic polynomials, but it will be less natural at least. Okay, proof. Step 1. I would do this projection with respect to all maximal ideals. So psi from OX to the product for all maximal ideals all OX quotient by M. This is injective. This is something we have discussed. Intersection of all prime ideals is radical, but in fact, from Hilbert-Neustein's, that follows that intersection of all maximal ideals is radical for finitely generated rings over C. So this makes sense, and it is an injective map. Yeah. Now step 2. We take phi is a map from OX to direct sum of OXI, where xi, it's for all I, are all irreducible components. of x. This is injective. Phi is injective because psi is injective and psi is composition of phi and something. Every time you take a projection to a maximum ideal, you can choose this maximum ideal, consider it as a point on corresponding xi, and factorize this first to this oxi, which is a quotient of ox by some ideal. So phi is injective because psi is factorized through phi. So psi is a composition of something and phi. Psi is injective, then phi is injective. Okay, but it also makes sense to describe the spectrum of this ring, and it is something we have discussed a lot. So coproduct of in the category of rings is direct sum, and coproduct of category of varieties is disconnected union. So spec of this ring direct sum of oxi is just disconnected union of all xi, and then you take this map and you put it to x, just each component goes to itself, xi goes to xi, and this is precisely our map. So ox goes to this or direct sum of oxi. This is the corresponding map of this pullback under this projection. Okay, now step 3. We choose linear coordinate change, as in this corollary 1, which is neuter normalization. And choose lambda generic. Lambda I, how there, I plus j, j plus k I generic. Then the projection pk to the first k coordinates from xi to c power k is finite. Good. This gives now a sequence of rings. You have O of x. So you have direct sum of O of xi. O of x is contained in there because this map is injective. And then this contains O of ck. These are functions which are pulled back to x. Functions on ck which are pulled back to x. And we choose it in such a way that this on each component, this pullback is injective to here. Because of this, this was our assumption. We we have chosen the projection to ck in such a way that on each xi it's finite. Well, anyway, so this from here to here it's injective, and this is intermediate. This is finite over this, so this has to be finite over this. because, look, this is finite over that. This is our assumption. But then something which is intermediate is also finite by because this is Noetherian thing with finitely generated model over OCK, and this is intermediate. If you have a submodel of finitely generated model, it's finitely generated. This implies that this ring is finitely generated. Yeah, was I clear in the previous with this picture? Good. Now we are going to, I'm going to recall something which we had like a few lectures ago. It was about integral closure and when it is finitely generated. It's again a reminder, essentially. So I just collected pieces which we need to state and to prove the biggest, the most useful version of Noetherian normalization. So definition, if you have A and B, integral closure of A in B is the set of all B inside B, which are finite over A. In other words, that is, we have Ka of B. This is a subring in B big generated by A and small b. Is finitely generated as a model. And the sum and the product of finite elements is finite. It's something we proved already. In fact, it's the same argument as works for algebraic numbers. Yeah, and then if you have integral closure, so x A is integrally closed, if or normal, if A, the integral closure of A in the corresponding fraction field in K of A is A. Of course, this is not, this definition requires us to have no zero divisors. Otherwise, we don't have fraction field. But in a couple of slides, you will see a definition of normality which works generally, a normalization. So it's, you can modify the definition in such a way that it works for even when you have the zero divisors. Okay, and what we had last time was the example, this most important example, which I'm going to use today as well. So remark, the field of polynomials is integrally closed. Sorry, the ring of polynomials is integrally closed. This is because it's factorial, and every factorial ring is integrally closed always. Okay. Now we have the following useful theorem, which we proved using this number theoretic argument with trace, if you remember. So you have A integrally closed and Noetherian. And then you have K big over K small of A, find extension. And B is integral closure of A in this field. Then B is finally generated. Generated as a model. In fact, what is really needed for today's purposes and for general is that it is finally generated as a ring. But somehow it's easier to prove that it's finally generated as a model, even if the statement is stronger. So this is what we had in lecture 13. So the argument was that you have a subring of B with the same, you just choose a basis of B over K small over this smaller ring, and you generate a subring in B from this basis. And then you use, it would be finite as a model. And then you use the duality provided by the trace form to obtain some bigger submodel, which is dual to your smaller submodel. So your B will be intermediate between this smaller one and the dual, which is bigger one, which is dual. And the bigger one, because it's dual to a smaller one, it's also finally generated as a model. And then B is intermediate, so it's finally generated as well. This is the argument. It's sort of, I suppose, due to Dedekind, who realized how to apply these things for like discrete relation rings, and then it was applied generally for number theory, and it's sort of, in number theorem, it's sort of standard with traces. Okay, and this, there is an example. So you have, this is an important example because in a few moments it will be a general example for any algebraic variety. So example, you have K big. It's a finite extension of rational functions. So this is the field of rational functions, this finite extension. Then the integral closure of polynomials in this ring K is finally generated. We just apply this using the polynomials are integrally closed, and then you have finite extension, and it will be finally generated by this theorem. So this is the main example when you can apply this theorem. Well, main for algebraic geometry. For number theory, the rings of integers are more important. Okay, so now I'm going to define normalization. So the idea is easy. You have a ring of functions, regular functions on algebraic variety. So X affine variety. OX is ring regular functions. And OX hat is its integral closure. So we assume it's reducible. So that this ring of the field of fractions is well defined, and yet you can take integral closure. It's integral closure of O of x in K of x. The normalization is spectrum of this ring, but it is not yet defined because we didn't prove that this ring is finally generated. And this is what I'm going to do now. I'm going to explain finally generatedness of this integral closure. Okay, so we have this corollary. Okay, so what notation are here? Yeah. A is OX and A hat is integral closure. Then A hat is finally generated. So this is what I'm going to prove now. And it's not very hard as long as we have already done everything which is needed. So the main abstraction why we couldn't obtain it in lecture 13 was because we didn't have Gauss lemma. So the argument is based on this example, which in turn uses Gauss lemma. So step one. And of course, we need this finite dominant map, which was constructed in the last lecture. So you have X to CK, a finite dominant map, which exists by corollary 1, which is our the first version of Noether normalization lemma. Okay. Yeah. It says A is integrally closed, but it should be A hat. There's a misprint here. So A hat is integrally closed. Contains OCK and same field of fractions. Yeah, sorry, A should be, I'm not, I can't read what I wrote. So A is integrally closed. I didn't define A, so A is integral closure of C of the polynomial ring in the field of fractions of X. So first, X is finite over this. So this means that the corresponding fields of fractions are the same, because if you have an the field of fractions of, you have K of X is finite extension of K of Z1 dot ZK. This is because this map is finite. Sorry? A is integral closure of the polynomials in this field of fractions. A hat is did I erase it? No. A hat is integral closure of A in its field of fractions. So a priori, A is contained in a hat, but we haven't proved the converse yet. It's still true. So I want to say tell you the properties of this ring A. It's by construction integrally closed, because it's integral closure of this and that. Integral closure is integral closed. Integrally closed, well, it's integral closure of something, it's field of fractions, so it's integrally closed, first. And second, it has the same field of fractions because, in fact, it contains OX. OX is finite over CK, so it contains OX. So A. So this finite extension, and so A contains OX and has the same field of fractions and integrally closed. So step 2. If we prove, yeah, that's finite. So A is finite over OCN, CK, by this example. Let's call it example 1, for instance. This example tells you that if you have a ring of polynomials, you take finite extension of the field of rational functions, you take integral closure, it will be finite, finitely generated as a OCK model. So it remains to show that A is equal to A hat. That's all. If we prove that, we obtain that A hat is finitely generated as of CK model. Okay. Yeah, you have this A sitting inside or X sitting, and it contains the polynomials. And by construction, this is finite over that, right? Then A is finite over OX, because this is bigger. Means if it's finitely generated over this ring, it's automatically finitely generated over any bigger ring. Finitely generated is just you have a set of generators over the smaller ring, then they generate everything over a bigger ring as well. Okay. And I hat is smallest. Yeah, is smallest finitely generated well, it's a set of all finite elements, set of all or X finite elements in K of X. But all elements of OA are finite. This means that A is contained in A hat. And converse is also clear because all elements in A hat are finite over OX, so they are finite over this. And you have converse inclusion as well. So A hat is, what is it? It is an integral closure of OX inside its field of fractions. But, so all elements in A hat are finite over this. That's it. Again, you just have two different integral closures, but in fact they're the same, because A is integral closure of this in the K, in the field of fractions, and I hat is closure of this in the field of fractions. So one of them is for free, contains another. And the opposite inclusion follows because all elements in A hat are finite over this, and all elements of A are finite over this. So all elements there are finite over this and this, all elements of there are finite over this and this is, so A is all elements in field of fractions which are finite over this ring. A hat is all elements over in the field of fractions finite over this field, but these finiteness are equivalent. If something is finite over this ring, it's finite over that ring, and vice versa. Because this is finite over that. So if you have something which is finite over this, you just choose the set of generators that will be finite over that ring. Conversely, if something is finite over that ring, you choose generators of this over this ring, and then you add generators of that over that ring. This is something we had. If A is finite over B, B is finite over C, A is finite over C. It was in the beginning of last lecture. So this is how you do it. Okay, now we can define normalization. Define. You have X is a affine variety. A hat integral closure of OX in K of X, then spec of A hat is called normalization of X. So let me give examples. This is the most standard and basic example that everybody has when anybody speaks about normalization. You immediately have this example. So you have C of T squared T cube, which is the same as C of X and Y, with generated by relation. X is T squared, Y is T cubed, so X third is Y squared. This is the same ring. From here you map to there by taking T squared to X and T third to Y, and from there you map to here by taking X to T squared and Y to T, and you check this relation. Okay, but however, C of T, you can divide this by this, and is a field of fractions, and K of, this is A, is a field of fractions of A. And then I claim that C of T is normalization, is integral closure of this A in K of A. Well, first it's integrally closed already. So if we prove that this integral closure contains T, we are done. But then T is equal to X, Y by X. It's this generated by this generated, and then T squared is equal to X. So T is a root of monic polynomial, and it belongs to a field of fractions. This means that your T is contained in the integral closure of this ring. Am I clear? Let me repeat. So you have this. You have two representations of the same ring. So T is X squared, Y is t square is x, and t cube is y. And this is the only relation which generates this ring. And then your standard map is from here to here by that, by this, well, from here to there, you take x to t squared, y to t cube. And then the converse map is you just take any power of t and map it to the appropriate power of x and y. Using this, you will see that it is well defined. Clear so far? Now you have this t equal to x by y by x. It doesn't belong to this ring, because ring starts from t squared and t third, but it belongs to the field of fractions. But then t squared satisfies x, because t squared is x by this, well, yeah, by this relation. So in other words, y divided by x squared is y squared divided by x squared, right? But y squared is x cubed. So this is x cubed by x squared, and this is x. This is why in this ring we have this relation. This relation, t is its field of fractions. So you have an element of this field of fraction which satisfies monic relations. And it should be added to this ring if you want to take integral closure. But after you added this ring, you obtained integrally closed ring which is C of t. We know that it's integrally closed because it's factorial. And this has a geometric interpretation. So the corresponding, so look at this. You can think of this as a curve, one-dimensional subvariety in C squared, and then it's parameterized by t, and it has singularity near 0. This is x, this is y, and it has singularity because this is, I mean, just make a graph of this function, of this relation, and you will have, so this is the way you, something like that. So it has a singularity and 0. And then you have, let's call this C. C is a curve defined by x squared, x third is y squared. And then you have a map from C of t to O of C. Oops, sorry, converse. It's from O of C, which takes x to t squared and y to t third. This projection corresponds to an map from C, from the curve C to A1 to the affine, one-dimensional affine space. Sorry, converse, from one-dimensional affine space to C. So if you have a map from this to that, you have an opposite. This is a pullback of the regular functions from that, and what it is just parameterization of your curve. So your curve is smoothly parameterized. It's actually bijective. So this map is bijective on the level of points, but it is not bijective on the level of regular functions. There are more regular functions on this than on that. One should think of that as a resolution of singularities. In fact, if you have a regular complex curve, one-dimensional, one-dimensional singular complex curve, one-dimensional variety, like that, then its normalization is always smooth. Maybe we won't have time to prove it. It's not hard to prove. The hard part is to define smoothness on the level, on the language of algebraic geometry. But then it becomes almost immediate that normalization in dimension 1 is just resolution of singularities. Okay, so I defined normalization. Before I go on, let's make an interval. Nós temos intervalo para 5 minutos. Vou continuar. Okay, so what I did, I defined normalization. I gave an example. Of course, not every, there are lots of singular varieties which are normal. And for example, you can consider, for example, as a singular but normal variety, you can again consider the quotient, C square quotient by plus minus 1, which is spectrum of even functions. Even. And then you can check that if you have a relation inside well, you can, it's not hard to see that it's integrally closed, but it is singular because if you, well, can check it is singular as well. So this was an example of something which is singular, and of course all smooth things are normal. This is again a non-trivial theorem but we didn't define smooth things, so I can't prove it, even state it properly because I don't have a notion. Okay. So I'm going to tell you another version of normalization, of the definition. First, it's more functorial, and second, it makes sense even in a situation when you don't have the fraction field, when your variety is non-reducible. So the first observation is that if you have a, remark, suppose I have a map, well, normalization, x to x1, normalization is birational, meaning that they have the same ring of fractions, and finite, because it's finite. Moreover, if you have some other ring, x to x1 and x prime to x1, and they're both finite and birational, you would have this would be factorized. So you would have a map from x to x prime. This is because OX prime is contained in OX. Indeed, it's finite. This map is finite. So all elements here are finite over OX1, but they belong to the fraction field because this map is birational. But then all elements which belong to the fraction field and are finite over OX1 belong to OX. So this means that all regular functions on OX1, in fact, are regular on OX. This implies that you have this map. Just because this ring OX contains OX prime. This gives you this map. And it is, of course, this diagram is commutative because the corresponding ring of fractions is contain all these three rings, and so it has to be commutative because they are contained in the same ring. Okay, so this gives you sort of functorial property of normalization. Let me do it slightly more formally. So we have a corollary, which will become a definition once we pass to non-irreducible varieties. So corollary. So normalization is a finite birational morphism x prime to x such that for all finite birational morphisms phi from x double prime to x, the map phi can be factorized so there exists nu from x prime to x such that the diagram, you have x prime, this is our normalization, it goes to x double prime, and they go both go to x, is commutative. This is what is written there. Okay, if you want to get rid of assumption that your manifold variety is reducible, you just define birational for non-irreducible as maps. So birational map is a map which induces isomorphism of equal functions on each irreducible component. So you have a irreducible component in x prime, goes to a irreducible component in x, they are bijective, and on each irreducible component it induces isomorphism of the fraction fields. Then this makes sense, and in fact, this would give you normalization for the singular, for varieties which is not reducible. So it's not hard, because as we just discussed, you have the finite, if you have singular not reducible variety, x is a union of xi, then you have a disconnected union of xi, which is mapped to x, and this is a finite map, as we have discussed. And then you just normalize this. You take disconnected sum of normalizations of all xi, which is mapped there, and then you can check that this property is satisfied. So this gives you normalization for guys which are not irreducible. Okay, and in fact, everything can be made even more functorial, more categorical, if we define the category. Define category C of objects are pairs. X prime, so fix x. It's a fine variety. Are pairs from x, it's a phi prime, or mu prime, where mu prime from x prime, this is a morphism which is birational and finite. And morphisms in that category is from x prime mu prime to x double prime mu double prime. There are commutative diagrams. You have x prime goes to phi. Phi goes to, using phi you go to x double prime. And this are your maps mu prime and mu double prime to x. This is morphisms from this to that. Okay, and then normalization. X hat is initial object in this category. Just because of this corollary. if you have any map of this type, where x prime is your normalization, x double prime is something, you always have this phi, which is unique. And this implies that the normalization is the initial object. It gives you, in that category, in particular, it's uniquely defined using this categorical notion. Am I clear? Clear? Again, you have, so what does it mean? Finite birational. It's just a subring in a ring of functions. So you have a subring. So finite birational map x prime to x double prime to x is the same as finite subring intermediate between OX. You have OX is contained in A, it's contained in K of X, and it's finite over OX. So it's finitely generated as OX model. And the normalization is the biggest of such rings. This is why it is initial object. It contains all of the rest. So this is why you have this unique map from normalization to anything else. This just means that OX double prime is contained in all X prime, and this gives you a unique map compatible with these projections. Yeah. Well, normalization is a canonical birational model always, except that it can be singular, but for a curve it's smooth. So every curve is canonically birational to its normalization, which is smooth. And generally, normalization is a nice object because it's that canonical. It's very, very functorial. I mean, almost any reasonable operation on rings which it would compute with normalization. It's not things like completion and tensor products compute with normalization, which is not obvious, but it is a theorem of commutative algebra. Okay, now I'm going to noter normalization. Before I'm doing that, let me give you a new proof of the theorem which we have discussed. It was an exercise, and I guess there could be people who solved it. But now we can prove it using the whole machinery we have developed. Just for fun, because we already more or less know this. This is a very non-elementary argument which proves a very elementary statement. So it can be considered just as fun. Okay, proposition 1. We have infinite ring. So K, characteristic 0 is not needed, but what is needed is that K is infinite. V is a vector space. And now we have W1, Wn. Subspaces, proper subspaces. Then V is not equal to a union of all Wi. Okay, so the proof, well, it might happen that some of WR are smaller dimension. Let's increase them in arbitrary way that they become codimension 1. It's possible. So assume Wi have codimension 1. can always assume that by adding more vectors to Wi. They would only increase, so if this is, which become true, it was true before. Okay. Now we have the algebraic variety. So Wi is the set of all x such that mu I of x is equal to 0. And you have algebraic variety x, which is union of all Wi, which is 0. It's given by equation. Product of all mu I is equal to 0. And we want to show that this algebraic variety, which is a divisor, is not everything. Everything. There are points which don't lie in this divisor. So need to show that x is not everything. Okay, we have a we have a projection from our space. Here it was V, but somehow here it's already double. Well, it's a mess. You have a projection from x to Cn minus 1, which is finite. This is our version of Noether lemma. And we had it. I mean, in the second slide, I explained how to do it for something which is, this is clearly not irreducible, but we know how to do it. Sorry? Are you sure that you don't use algebraic at all? No, not yet. No, we don't actually use it at all so far. What we use here is this. Well, on the way, it also uses that for if you have a. Who knows? Maybe. Doesn't matter because we still. I'm going to apply that to situation overseas. So I don't think it uses it, but if it does, we don't lose anything. Anyway, you still have this finite map. This is linear projection. Linear projection. How to do it? It's for this particular example, you don't actually even need it. So since we are in that situation, what we need is a projection which you have this Wi. You want a projection which is finite from Wi to C n minus 1. So this means that the anyway, it's just a linear function. It's a linear functional which is non-zero on this of these subspaces. And then you have this projection from X, which is union of all these guys, to by, let's call it pi. And since it's finite, the preimage of a point is finite. But then the preimage of a point is a line, because it's a projection. So there exist points on this preimage of a point which don't belong to X. Because here we use Noether lemma. We project it to something, and we know that preimage of a point is finite if your map is finite. This is something we had proven already. Of course, this is semi-cheating because this is such a simple statement, and we prove it using some general observation. On the other hand, it's good because the same would work for any divisor. If you have a divisor in Cn, you again apply a Noether lemma, you project to Cn plus 1, and you prove that this divisor is not everything, which is useful. So you have a divisor in Cn. You modify your coordinates using this trick which we had in such a way that it projects finitely to Cn minus 1. Then preimage of a point is finite. But the preimage of a point is a line, and the line is in one-to-one correspondence with k, and k is infinite.
Why the preimage of a point is a line?
Because it's projection. It's projection from Cn to Cn minus 1, linear projection. Yeah, yeah. Okay. So of course, it's much easier to do it for this concrete example than to use the whole machinery, but it's just an illustration of how you can apply the machinery. Okay. Now I'm reminding you the primitive element theorem because we are going to use it. And it was sort of left without much comment before. So we have a lemma. You have a ring A, which is direct sum of several copies of K. Then A contains only finitely many subrings, subrings. It contains finitely many subrings. One of them is not proper, so there's finitely many proper subrings as well. K subalgebras is better to say because subfield, there could be many subfields. K subalgebras. And proof. Okay, if an idempotent EI, E is irreducible. If E is not equal to E1 plus E2 with E1, E2 equals 0. And any idempotent which is unit in a field is irreducible. So generators, unities in Ki in these fields are irreducible. Because if you have this decomposition, then you would have E1 is equal to E1, E2 is equal to E2 by these two relations. But then multiplication by E, if E is a unity in a field, is surjective on this field. And the field doesn't have any non-trivial idempotence because it has no zero divisors. So this means that every idempotent in this direct sum of Ki is a sum of unities EI, just sum of EIK, EIJ from J equal to 1 to some number L, where EIJ are generators idempotent generators in these fields ki. Okay. Now suppose you have some ring. We already proved that every ring has idempotent in it. So it would contain subfield ki, then you can use induction. Just decompose everything into, you find an idempotent and you decompose everything into sum of idempotents and obtain that every subring of this direct sum is just some smaller direct sum of some components ki. This is something we already discussed that. Just decompose everything and project. Am I clear or not? Should I repeat? This is a theorem which we had in the lecture about idempotence. Should I repeat it? No? Mitya? Okay, the idea is simple. You just, you start with, you prove that every subring is, in fact, it has a unity, which is an idempotent in that ring, but there are finitely many idempotents. Because every idempotent, if you have idempotent E, you decompose this E as a sum of EI, where EI is this generator, the idempotent in each field, unities in each field. So, and they're indecomposable, so this idempotent has this form. Yeah, I repeat a proof which we had. I just repeated to remind. Okay, and this immediately implies that if you have a field, so corollary, if you have K over K small, find extension, then the number of subfields between K and K big and K small is finite. And proof, you just take a product, a tensor product of this K with K bar over K small is a direct sum of several copies of K bar, where K bar is algebraic closure. And every subfield gives you a subring here. The different subrings give you different subrings, but there are finitely many subrings in that algebra. Finitely many. And another corollary is primitive element theorem. So corollary, K over K small is finite, extension, and separable. Separability is needed to have this product decomposition, because it's quite possible that this product will be would contain nilpotents unless you have separable extension. So primitive element theorem is false for separable extensions. It just fails. And then K is K small of alpha for general alpha in this K. This is because when this fails precisely where alpha is contained in a smaller subfield. There are finitely many subfields, and you can apply this proposition. So general element is not contained in any subfield, and this is precisely the element which generates K big over K small. Make clear? Clear. I can repeat. Look. So you have let's number all subfields. There are finitely many. You take K without the union of all proper subfields. And you take alpha inside this complement. Then K small of alpha is a subfield. Right? It's a subring. Well, every subring in a finite extension is a subfield, in fact. But you can generate subfield anyway. So this is a subfield. But it cannot be proper subfield because all proper subfields are removed. Alpha doesn't belong to a proper subfield. Then this is everything. Because it's a subfield but not a proper subfield. So it's K. So what you use that this complement is non-empty, and it is non-empty by this proposition that if you remove in a vector space subspaces, it's always non-empty. Am I clear? Okay, good. Thanks. Yeah, this is Amy Nutter handwriting. She wrote a letter to her colleagues, lots of them, and this is one of the such letters. It was much earlier than the Nutter theorem, because Nutter proved her theorem. This is a biography of Amy Nutter with a very strange picture. Well, one of them good, and the frontispieces, of course, it's terrible. There's lots of discussion online whether this second picture is right or not, but it's definitely colorized. The original is black and white. Anyway, so Amy Nutter proved this theorem in 1926. So let me state it now. And this is very similar to this primitive element theorem. It's just like a version of primitive element theorem, but for varieties for finely generated rings instead of fields. (1926). Okay, so you have X inside Cn, irreducible, and normal. And a transcendental degree of X is K. So this means that if you have this projection to Ck, there is a finite projection to Ck somewhere. Okay, then there exists a variety x1 inside C power k plus 1, given by a single polynomial. So C k plus 1 with coordinates z1 dot dot zk and t. And this x1 is a set of all zeros of all z1 dot dot zkt, such that p of this z1 dot zkt is equal to 0. So it's given by this single polynomial where pt is a monic polynomial. It belongs to C of z1 dot zk of t. So it's a polynomial on the variable of t with coefficients in this ring of polynomials is monic. And x is normalization of x1. So it's almost like you can describe any variety by a single equation, like a divisor in C k plus 1, with the exception that you have to pass to a normalization after this. So it's almost like uniformization of a variety, except that you need to do a normalization. Okay, of course, what I described to you in the beginning was a version of that, except that if you don't assume that x is normal, you would have another variety, and then, yeah. Well, you can state it without the word normalization. I'm not going to do it now, but I did it in the beginning. Okay, so step 1. We have consider there exists by corollary 1 the neutral normalization. There exists a fine projection, dominant projection from x to c power k. And we choose coordinates. So we choose coordinates z1 dot zn such that this projection pk to first k coordinates is found. This you can always do by slightly adjusting your coordinates. Okay. Now consider the space W. Let W. It's a subspace in O of k, of x, generated by the rest of coordinates, z k plus 1, dot 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 z n. Then, obviously, the field of functions, the field of fractions, k of x, is generated by W over O of ck. Okay, so I claim that there exists tau in W such that k of ck of tau is k of x. This is a version of primitive element theorem, except that now we want this tau, the primitive element, to belong to this fine-dimensional subspace. Okay, why it is so? Look, W generates k of x. This is, we know, because this is a coordinate embedding, so coordinates generate the functions. So W generates this. And then, indeed, intermediate proper subfields, you have K1 between K of x and K of ck. This finite extension, there are finitely many proper subfields, intersect W in k-dimension bigger than at least one subspaces. over k of ck. Indeed, W generates everything. So general element so it cannot belong to a proper subspace because W generate k of x, and these are proper. Then you take W without all this union of ki, it's non-empty. This is the same argument as we had before, except that before we had it for general field, now we have it for W as a vector space, or just a set, it doesn't matter. It's non-empty, and then it implies that for each tau inside this W without union of ki, k of ck of tau is O of x. This will be our elements which we need. I mean, what we wanted to do in the case of for Noether theorem, we wanted to add an element which would be obviously algebraic because it has the same algebraic dimension, add an element to a polynomial ring to obtain a ring which is up to some normalization the same as our O of x. Now we at least can do it with a field. So you obtain a field which is by adding a coordinate. Okay, the next slide. Okay, so we have chosen this coordinate tau. This is no longer needed. So step 2, we take a projection. Step 2. We take a projection x to ck plus 1, taken x to z1 of x dot zk of x and tau of x. So this is now this projection induces isomorphism on the fraction fields. So so on, since tau generates k of x, and it is finite extension of or k of k of ck, tau is a root of a polynomial p of t coefficients in k of ck. In fact, we can always choose a coordinate properly using again the Noether normalization, which was like corollary 1 in the beginning of the lecture, such that the coefficients will be in fact polynomials. And this will be monic. So it's not only polynomial, but of a monic polynomial. This is because the projections for general choice of coordinate projections finite, and tau could be chosen generally. Of course, we might need to choose to change the coordinates here and we do this linear change of coordinates, which we always have to adjust the coordinates a little bit. When you return to that, when you need to do this coordinate change in a prescribed way, some fixed way, it's hard. So, but at the moment we don't need it. Okay. So, in the end, we obtain a space x1, which is spec of C of z1 to zk of tau, where well, I write this tau, but what I mean, it's a subring in OX. And OX is finite over this. So this is our x1. It has these properties. And then k of x1 is k of x. This is because it's a primitive element. Tau is a primitive element which generates the same field of fractions as x. And then x is finite over ck, x1 is finite over ck, has same fraction fields. But then OX is normal. So, sorry, x is normal, which gives us the following diagram, which we already had. It was x goes to CD, x1 goes to CD. This is a projection. But then this projection is in fact a normalization of x1, because x is normal, it's finite, and has the same fraction field. So x is normalization of x1. It's an integral closure of OX1 in its fraction field. They have the same fraction field, it's integrally closed, and contains OX1, and it's finite over OX1. So x is finite over x1 because x1 is an image of this under projection, or because in fact x is finite over CD and x1 contains OCD. So it's finite over x1 for two different reasons, and it has the same fraction field. So it has to be normalization. Okay, so I think I'm done with the Noether normalization theorem, and yeah, it's a bit like uniformization theorem. Let me explain how it is used. So suppose you have a it used a lot in part of things like so you want to represent your variety by something that makes sense, which you can describe. And I already mentioned Riemann, who defined before he defined, well, he never defined manifolds, but in fact he had a definition of manifold using what he called Riemann, well, what is now called Riemann surfaces. And it is, you have a C, you have a function which has multivalued, f multivalued. And then you take it's not well defined on C, but it's defined on certain ramified cover of C. So you have a ramified cover, and you have your manifold projected to C. Generally, it's n to 1. It's like locally a diffeomorphism, but in special points, it's not n to 1. It's 1 to 1 or 2 to 1, something smaller. Like, typical example is you take a Riemann surface for root of nth power of t. It's the corresponding map is just a map from C to C, taking t to t power n. This so the corresponding n to 1 map is a Riemann surface for this multivalued function. Okay, so what Noether's theorem gives us? She gives us this theorem gives us a representation of any algebraic variety up to certain normalization as a multi-valued function. Namely, you have this polynomial p of t with coefficients in O. So you can consider this polynomial as a polynomial with like for each point z1 dot 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 zk, you can evaluate this polynomial. This would give you p of t evaluated in z1 dot dot zk. It will be polynomial in c of t. So for each point, you have precisely k solutions of this polynomial equation. So your x1 is n to 1 ramified cover of ck. Of course, some solution of these polynomials can overlap and join, but it's monic, so it has precisely k equation with some multiplicities. Your equations, your solutions overlap. It just means that they have extra multiplicity, and this corresponds to having ramification points for this ramified cover. So this is the meaning of the Noether normalization theorem. It tells you that every affine variety is ramified cover of CD up to normalization. Thanks. Obrigado. Eu terminei.